Balanced binary search trees and hash tables are both used to implement the abstract data type map. We will describe this abstract data type and examine one application that implements a map using a hash table. Then examine how Java implements maps and summarize some of the considerations about which implementations are best for any given application. Let's consider the map as an abstract data type. Like all data structures, a map is a collection. Specifically, it is a collection of key-value pairs. Dictionary, key table, and associative array are all synonyms for a map. The origin of the term map is from mathematics. A map, which is a synonym for a function, maps values in the domain to those in the codomain. With the map data structure, the set of keys are the domain, and the set of values the codomain. Maps can be implemented in many different ways. Balanced binary search trees, which include AVL trees and red-black trees, which we discussed previously, are two types. There are other variations as well. Hash tables are another possibility. A map constructed with a hash table is one of the implementations provided in the Java Collection Framework. Unsorted and sorted lists are another possibility. Previously, we saw an example of a sorted list used to implement a set. A similar implementation could be used for a map. But because both are less efficient than other possible choices, they are typically not used for this purpose. As was true with sets, some implementations are sorted structures and some are unsorted. There are four primary operations in a map data structure. The get operation retrieves the value given the key. The put operation puts the key value pair into the map, provided there is no pair with the same key already in it. The remove operation removes the key value pair given the key, provided it is in the map. And the contains operation returns whether the map contains a key value pair with the specified key. Next, we will examine one application that uses a hash table to implement a map. The hash table class has been defined so it could implement either a set or a map. Because it supports all the operations of any collection, we elected to make it implement the collection interface. Because it is intended to work with either a set or map, we made its generic type parameter keyed, which only requires that elements contain a key that can be retrieved. The hash map is the class we will be testing. It implements the map interface. The reason for having it implement this interface is so that if we decided to provide a different implementation, we could easily substitute hash map with the other implementation. The generic type parameter of the hash map class is map entry, which is a record that defines a key value pair. Because it allows a key to be retrieved, it implements the keyed interface. The last class in this diagram is hash map GUI, which defines the interface that allows us to test the hash map class. Before we run this program, let's look at how the hash table is represented and one of the methods, the add method that inserts a value into the table. In this implementation, we are chaining the collisions in a singly linked list. As we have done in the past, we define the node of that list using a nested class. The representation of the hash table itself is an array of head references to a collection of linked lists. The add method is given the element to add and returns whether it succeeded. It first checks whether the key is already in the table. If so, it returns false to indicate failure. The contains method calls the find method, which computes the hash code and leaves the resulting subscript in the instance variable index. It also leaves behind a pair of pointers, previous and current, that are needed by the remove method. It allocates a new node of the linked list, stores the element in that node, and it sets its next reference to the pointer that was previously the first node in the list. This has the effect of inserting the node at the head of the list. Because the order doesn't matter, insertion at the head is done because it's the simplest. Using the subscript index that resulted from the computed hash code left behind by the find method, the head reference to the linked list at that index is updated. Finally, true is returned to indicate success. In our implementation, one feature that we have not included is expanding the table and rehashing when the load factor is exceeded. Let's run the program and test out some of the operations. So we'll start out by putting some things into the table. So in our example, the key is going to be the name, and ID number is going to be the value. So we'll put one of those into the table, and let's put in one more. A second one, and choose some other key. Make sure I pick something different. And then next, test get. So in the case of get, we should supply a name, and it should give us back the associated key. Another thing we can test is the contains method. So if we ask the question, is there a key value pair with the key Mary? It will tell us yes. If by contrast we try one that we know isn't in the table and say, does it contain Bill? The answer comes back, no, it's not in the table. And let's see, there's one more we need, which is the remove. So let's ask it to remove John, which we put in, and then come back and check, just to be sure that it worked. We'll check to see whether John is in the table, and it is not. So I think with that little scenario, we've tested most of cases. Perhaps there's one more we could test. Let's put in, we knew we had Mary in there, so let's put in Mary and then put in something else, because we shouldn't be allowed to have duplicate keys. So it tells us Mary was already in the table, and it doesn't allow us to enter it. Okay, so next, let's consider what implementations the Java Collection Framework provides and how its classes and interfaces are organized. The map interface sits at the top of the hierarchy. It includes methods similar to the ones just mentioned, but it includes several others as well. The abstract class, abstract map, is the abstract class that is ultimately extended by the three primary implementations. It contains both abstract and non-abstract methods. Among the more interesting methods is the one that returns a set of all the keys currently in the map, and one that returns a collection of all of the values. The sorted map interface is the interface that is the one implemented by the tree map, the only sorted implementation. Although the intent is that the key type parameter be a class that implements comparable, the interface does not specify that constraint. Consequently, it's possible to declare a map of this type with a key that's not an ordered type, and no compilation error will occur. Instead, a class cast exception will be thrown once an attempt is made to perform one of the operations, such as a put. One might question whether this design was the best choice. The tree map class is the sorted map class that is implemented using red-black trees. The hash map class is an unsorted map class that uses a hash table. The linked hash map is an extension of the hash map class that maintains the insertion orders of the elements. We conclude by comparing the efficiency of the various implementations and what considerations should affect which ones to choose. When using a balanced binary search tree implementation, regardless of the specific type of tree, the operations to insert, remove, and find an element are logarithmic. With a hash table representation, the same three operations, insert, remove, and find, are all constant. Although execution in constant time is faster than logarithmic, log n grows so slowly it is not much worse than O of 1. As a result, the choice between them is not likely going to be based on efficiency considerations. So what other factors should we consider when deciding which one to use? If the key type is not an order type, then a hash table is the only choice. Order types are, of course, ones that extend the comparable interface. Because the object class defines the method hashcode, all objects are hashable. Because they have hash codes, there's no restriction on the type of the key, provided it is an object. Recall that in Java, a generic class can only be instantiated for objects, so primitive types are not a possibility. Not all languages have that restriction. The final consideration is whether keeping the data in sorted order is important. If so, a balanced binary search tree representation is the only choice.